Hey everybody, Dave Lindberg, THD Podcast again. And today we wanted to just talk about different magnet chemistries and how they impact performance on speakers and different aspects that they influence the motor structure and the performance of that motor in a transducer application. So again, as always, Simon's joining us from Japan and lots of neat things to talk about. Hey Simon, how's it going over there today?
Hey Dave,
All
pretty good today. Yeah.
All good. All right, so yeah, let me just kind of highlight what I know about speaker magnets. So basically, there's two major technologies or chemistries, let's say. One's a ferrite, or sometimes called ceramic, and those are typically larger magnets. So I have an example. This is like a ferrite magnet here on a classic kind of soundbar speaker. And then like low-profile speakers will use something called neodymium, which is a rare earth metal. So it's not necessarily hard to find, but the process of extraction from the earth is a little bit dangerous. So there's not too many mines around the world that are extracting this material. So this is actually an exciter for a flat panel speaker. And these will typically always use neomagnets because they need to be low profile. So neodymium is sometimes up to 20 times stronger in its magnetism than ferrite. So that's kind of a reason they're typically used in low-profile speakers. And so then that kind of leads into something I wanted to ask Simon is Neo something that's almost exclusive in headphone drivers, or do we find some headphone speakers that might still use ferrite or something larger? I guess that's kind of
my guess would be there'd be zero headphone drivers using a ceramic or ferrite magnet. It's all neodymium. And it's just because it's a size issue, size and weight as well. So you get the magnetic field strength in a much smaller volume, and that's what really counts. So the thing you might say, well, why not just use them for big drivers too? Well, because you can save a lot of money by using a ferrite driver, and because you have the space, you can get the same total magnetic field. You just need a much larger volume of magnetics.
Okay, that's actually
so the headphone drivers can just use a small button. Yeah.
Right. So that's actually kind of interesting that you bring up the cost of ferrite versus neodymium, which is dramatic. Not exactly sure the market price on these things. Neodymium does fluctuate quite a bit. It is heavily used in automotive engines. So if there's a big drive for that supply, it can impact the speaker price around the world. But I just wanted to show an example of like the total motor structure. So this is a ferrite magnet, yes, with a particular cone material. But then you can see the difference in the ferrite cost here is it's roughly about half the amount of magnet in something. And what the designer did is they were able to use a lighter weight cone material. But actually this was all stemmed because originally this driver was meant to fit in a soundbar where for the center channel, there was some electronics. So they had to use a neodymium magnet on the center channel. But in reality, by switching to a lighter weight cone material, reducing the ferrite, they were able to fit in this ferrite magnet and the electronics. But the interesting thing is the system, the overall system. So it was a 5.1 soundbar system. So they were actually, by removing the neodymium from the center channel, they were able to reduce the speaker costs overall in the entire system just because of the cost of that one driver. Yeah. So to me, that really was a big example of the difference in price between Neo and ferrite. So that's kind of my perspective on pricing.
So when you have a magnet system, let's say like the ceramic one, it's actually a donut piece. And you have this magnetic material here, and then you put a steel, it's called a yoke or a T.
Yeah.
There, and you put another piece of metal on top. Actually, I should have drawn this one a little bit higher. Put another piece of metal on top, a donut on top like that. And then all the magnetic field gets channeled across this gap here and turns it into this magnetic circuit. So actually the limitation that you end up with is how much magnetic energy can you cram into this material. So that steel is quite important too, how much magnetic flux you can put into the steel. So when you're talking about a big speaker or a subwoofer or something like that, you can put as much magnetic material as you want in here, basically. There's no limitation. But like you say, when you're a bit jammed for space, you either have to go for neodymium or you have to find some other way to recover that lost energy, let's say, that you lose by cutting down the magnet size.
Right. So yeah, I also have some other drivers here I wanted to show that almost exclusively use neodymium. So these are actually the BMR drivers. And
right. Yep.
they're using a slight, I would say it's, I'm reaching out for some advice here, Simon, but I would say it's because they're using a honeycomb and paper sandwich structure as their diaphragm. So it's a flat diaphragm that's actually a honeycomb with two skins of paper. And so it's got a bit more mass. So they actually need more energy shoved. So they need a low profile magnet, but something that provides more energy. So I think that Neo is sometimes, like I said, 20 times more powerful than ferrite. So using a Neo magnet is actually giving more shove and helping to compensate for the extra mass in that diaphragm. Here's a larger one. Same thing. That's a big chunk in Neo there. So this is actually about a $10 driver right there for a 3-inch driver, which is considerable, actually.
Yeah, you have the old formula F equals BIL, where F is the force that you have a voice coil here that's connected to the diaphragm, whatever it may be. And the force that you get out of the circuit depends on the current, so that's your electrical input, your amplifier, the length of voice coil wire, and then B here is the magnetic strength. So if you want to get more force, you can increase B, basically, to get more strength. So that's what you might do by putting in a neodymium. But again, you're going to hit the stops in terms of how much flux energy you can get into the surrounding metal before it sort of limits out.
Right. Okay.
The other factor too, of course, is the amount of heat. So if you're talking about a smaller driver, like the one, the BMR that you were just showing, I think it's about an inch or 2-inch thing, was it?
There's this one. This is a roughly 1 inch. I think it's a 30.
Yeah, that 1-inch one. See, when you're running that, the amount of heat energy that's going to come out of it is not as high as a big subwoofer or a low frequency speaker. So you can tolerate a smaller lump of metal. So the heat is generated by that coil as an electrical. Comes from the electrical current and so on. And you need to dissipate that heat somehow, and so it tends to go into the magnet structure. When you have a big subwoofer generating a lot of heat, you could put in a small neodymium magnet, but you still need quite a big lump of metal around it to soak up that heat. So you end up just using a ceramic anyway. But for the smaller stuff, where the amount of heat generation is not quite as bad, you can use a small neodymium.
Yeah, I believe that neodymium is one of the weaknesses of Neo, besides cost, is it's less resilient to heat. So would that be why they're using more metal to encapsulate it for heat dissipation? Because it's
quite possibly. I mean, there'll be a calculation in there, how much heat are we getting, how much magnetic flux, and finally trying to figure out the neodymium size that you need to put in.
Okay. Yeah, so I think just in general, it's this magic balance of size and cost and performance on how you select your driver. Sound bars, headphones, all these things that need to be thin, either to match TVs or to be comfortable and lightweight on your head. They're typically going to be attracted to a Neo magnet. But like Simon says, big things like subwoofer that might have heat or other issues, and actually, a lot of customers they pick up a subwoofer and it's lightweight. It kind of means it doesn't represent value. They expect a big speaker to be heavy. Actually, one thing I know is sometimes people develop products. They actually put dummy weights inside the speaker to make it seem more valuable, because the weight translates into a perceived.
I wanted to mention one more thing. You usually find that there's two types of structure. One One has the magnet as a donut ring, so that is what this is. The magnet is actually a donut, and then there's the metal part of the circuit goes up the middle and a top plate. The other one is where the magnet is the button inside and the metal is the outside. So these style are pretty much always ferrite, and these are pretty much always neodymium.
So is that what they call the T-yoke and the U-yoke? Is that?
Yeah, exactly. A T-yoke and a U-yoke. Yeah.
Yeah. Okay. Yeah, that's interesting. Yeah. One of our network friends here is a big T-yoke, U-yoke supplier in Guangdong. So we're going to have him on in a couple of weeks to talk about his speaker technology. So he can.
Oh yeah, that'll be great.
About T-yokes and U-yokes. Okay.
So then you have the grade of neodymium too, of course, where they start, and that relates to the intensity or the strength of the field. But a lot of the headphone stuff, because the diaphragm's very, very light, you don't have a huge concern about sensitivity, and therefore you don't really have a huge concern about magnetic strength. What kind of becomes more important is is getting a consistent level of magnetic field strength, so that all your products have the same sensitivity. Because the magnetic field strength will relate directly to the sensitivity that you get.
Right, and do you know much about what kind of variance you might get on that magnetic strength? Is because I know that they say that neo could be up to 20 times more strong in magnetism than ferrite, but what kind of variability and does that allow?
Actually, I don't know. I don't know what variability. Say if you ordered a lot of neodymium magnets, you assemble them into the driver and then magnetize them, and at the end of it, what do you get out? You may well get quite consistent results because you set a magnetization process where you put it into a machine and expose it to a very high magnetic field, and then that magnetic field aligns the neodymium poles, etc., and you get. So if you're using a consistent magnetization level, that might actually set your magnetic level for the neodymium rather than you hitting the limit of the neodymium.
Okay, cool. All right.
So therefore, you'd actually get a very consistent field strength.
Right. Okay. That's cool. All right. I'm kind of talked out for my expertise on magnets. I think we covered quite a bit on it. But I'd like to.
Magnets is an interesting one because it doesn't get a lot of attention. And I think part of the reason is it's kind of just at a fixed value. You put in this magnet, you get some magnetic field strength, and there's not much more to do with it. But there is quite a bit of detail that goes on there in terms of designing the right magnetic structure in order to optimize your cost and performance.
Yeah, I know that
that's often hidden away by a headphone driver manufacturer. So somebody will come along and say, my headphone drivers are 20 cents, and the other guy is 22 cents. You say, wow, the 20-cent guy is better. Is he better, or did he just use less magnetic material? So
yeah, that's a common kind of thing, and also the quality of the magnetic material can vary quite a bit with your suppliers. But I know that, like, historically in loudspeaker design and manufacturing, a lot of people say, one of the greatest innovations in loudspeakers is the introduction of neodymium magnets.
Right.
Most people will put that as the number one innovation in making better speakers. So that's it's kind of a big statement. And it's kind of a big statement. And then when you correlate it to the fact that nobody talks about magnets so much, it's kind of like maybe there's a lot more there to discover.
So there's other chemistries of magnets. Alnico is one that comes to mind. A cobalt one, I don't remember exactly the name. But the whole industry has just gravitated out to just neodymium or the ferrite ceramic magnets.
Right.
So for a while there, you were seeing some of these other ones coming out, but I think they get lost in no man's land because they're not very cheap and they're not very strong.
Yeah, I have heard about people making multi-magnet structures to kind of control the polarity to allow for better shove. So they actually take multiple magnets and they force them together to create control over polarity through the electromechanical structure. But I mean, that's just depends how much percentage performance you get improvement. because
Yes.
you're kind of reinventing the wheel at some point. So it really, looking for that next breakthrough in magnet chemistry or something to actually do something really innovative in the magnet space. So, okay. All right. Well, let's kind of table it today, unless you have something else to add.
Yep. No, that's good. Thanks, Dave.
That's good. Okay. So yeah, if anybody has some comments and they know more than us, we'd be happy to hear your feedback. So hit us down below and subscribe if you want to keep up with our somewhat regular little chats on audio stuff. All right. Okay. Thanks, Simon.
Thanks, Dave.
Okay. Bye-bye, everybody.